Okay, so this is lecture 10 now, computational complexity. I hope this week, so I don't know how many of you have looked at any of the recordings. It's been very, very hit and miss, as we say in English. I have not been setting them up technologically very well. So last week there was a bit of an issue about how I set up the Zoom format. Other weeks there have been other problems. Hopefully this week everything will be all right. Let me shut the door. If you want some air, just to keep the noise down. So before going into the lecture material, let me just talk a little bit about the rest of, well, the next 2 weeks before Christmas, how the course is going to be organized. So today we have a lecture with the last presentations. And then we're done with those. Then on Friday there's the exercise class as usual. Next week there's going to be a lecture, but it's going to be, so there won't be any presentations with it, and it's going to be a technical lecture, mainly on the proof that IP equals P space, this main result that we said, that I mentioned last week. So it's the proof that IP equals P space, which is a major result, and in a sense this is going to be the one of the major technical proofs of the course. But it's very, very technical, so the whole lecture is going to be about this next week. And this is material that is really important for people that are aiming to get a 10 on the course, but for other people, you know, it's up to you if you want to try to understand this technical proof. So it's basically a very technical lecture next week, and because of that, there aren't really any exercises that we can set for it. So there will be no exercise class on Friday the 24th of December. So there's no exercise class or lecture on Friday the 24th of December. We're also not going to have a lecture on Monday the 27th of December, even though it's officially a teaching day. And then again, there'll be no exercise class on Friday on New Year's Eve, which is, oh no, that's not even a teaching day. But anyway, let's put it down. But that's been given as a holiday by our faculty or by the university, I'm not sure which. Anyway, Friday the 31st of December. There's not going to be anything, but instead of this, there's going to be your homework exercise, which will be released either at the end of this week or the beginning of next week. So instead, in this period, there's going to be homework, and instead of lecture time, so there's the homework to do. Instead of lecture and exercise time, Danelle and I will make ourselves available firstly by email appointment, but then we can chat over Zoom or something like that. So, there will be consultations available for help with the homework if you wish. And then on Monday, the 3rd of January, we'll go back to usual. From Monday the 3rd of January, we'll go back to the usual lectures, exercise classes for 2 weeks until the exam break. 2 weeks, lectures, exercise classes, of course, without the student presentations. So I'm not quite sure how I'll do the last hour of the lecture on those occasions, but there are only 2 of them anyway. Okay, are there any questions about that? Right. Good. So what we're going to do this week is going to continue from where we left off last week. So last week I introduced this notion of interactive proof and the way, sort of protocol by which somebody, the prover that has knowledge of a fact, can convince somebody else, the verifier, that the fact is true, where very importantly the verifier can verify that efficiently. So the verifier is a polynomial time or probabilistic polynomial time machine. In fact, all of the ones we saw were probabilistic, and the verifier can efficiently verify that the fact is true. The prover could be more powerful in last week's scenario, but the point was how to communicate that quite complicated facts are true. Today we're going to look at a related issue, which is still how to communicate facts that are true, but we're going to go back to simpler kinds of facts, those that are in NP. So facts that have a certificate, so it's very easy to communicate their truth. But we're going to look at a very interesting kind of protocol where you communicate the truth without actually revealing any of the details. Without revealing any of the reason why it's true. You just manage to convince the verifier that it's true without actually telling them why, so to speak. So these things are called zero knowledge proofs. Because as a prover, we convince the verifier that the verifier, apart from learning the fact that it's true and being convinced that it's true, doesn't learn any other knowledge. And we're going to look at, in particular, at some little piece of technology that's needed to implement many zero knowledge proofs, which is of really incredible importance in computer science, really an enormously important concept, and that's the concept of a one-way function. That's so I'm going to motivate zero knowledge proofs by looking at, again, at the example, continuing the main example we were looking at last week, which was graph isomorphism. And let me put myself in the position of being a prover. Suppose I know that two graphs are isomorphic. So suppose P, that's me, knows that the two graphs G1 and G2 are isomorphic. Well, how do I know that? Well, I have an isomorphism between them. That's how I know it. So P knows an isomorphism from G1 to G2. So an isomorphism is a permutation on the n element set of vertices. Remember, this square brackets n was the set of numbers 1 up to n. So it's simply a permutation on 1 to n, such that, so an isomorphism is a permutation that permutes the vertices that maps one graph to the other. So such that if we apply, then I should give it a name, pi. So such that if we apply pi to G1, we get G2. So the point is, what does P need to do to convince a verifier V that P really does know an isomorphism between G1 and G2? So the easy thing to do, P can convince the verifier V. So remember this, we had this notation, P is the prover who knows the fact that V is the verifier that wants to verify that it's true. The prover is trying to communicate the fact to V. So P can obviously convince V that that G1 is isomorphic to G2 by communicating this permutation pi. As proven P, you're all the verifiers. I just tell you the isomorphism. We had an example of that last week. So by communicating pi. And that's fine. But then I'm telling the verifier the isomorphism. So the question here that I want to raise is it possible for me to convince you that the two graphs are isomorphic without giving you an isomorphism between them? And in fact, without giving you any more information other than the two graphs are isomorphic, other than that the two graphs are isomorphic. I mean, obviously I could just say the two graphs are isomorphic, but then you might not believe me. So I want to tell you in such a way that you have to believe me, that you are convinced yourselves, but you don't get any knowledge. So can P convince me? And obviously P can, because otherwise I wouldn't be raising the subject. So let's raise it as how can P convince me without leaking, let's say. So you know, leaking, your pipes leak, some water leaks out of them, but here I'm meaning leaking a secret. So the idea is this isomorphism, P knows it. These are two very important graphs, and he's discovered that they're isomorphic. He doesn't want somebody else to know that to know the isomorphism, but on the other hand, wants to convince them that they really are isomorphic without leaking this secret. Without leaking pi to V, or indeed without leaking any other information at all. And this can be done by P using a zero knowledge proof. You can do this using a zero knowledge proof. So without further ado, I shall describe the zero knowledge proof that P can use to achieve this. So I know I could put the board up and start on the backboard, but then we'll be covering it. And actually what I'm about to write down is more important than what I've written before. So I'm going to start here, and I want to keep this part. I'm going to present a zero knowledge proof that G1 is isomorphic to G2. So I'll put myself in the position of the prover. I want to prove this to the verifier while keeping the isomorphism that I know a secret. So a zero knowledge proof. And we're going to assume that G1 is isomorphic to G2 in order to tell you what the proof is. And so the starting point is that we're P, and P has the secret knowledge, knows an isomorphism. P pi such that pi G1 equals G2. If he knows this, that P wants to keep it secret, but wants to nonetheless convince the verifier that these two graphs are isomorphic. So it's again going to take it's going to be similar to it is going to be an interactive proof. P is going to say some things, verifier is going to respond, and so on. They interact with each other until they make a decision at the end. well, verifier makes a decision at the end. So P first, I'm going to put a number after this means P in round 1 of P. So P goes first in this case. Last time the verifier was going first. I mean, it doesn't really matter who goes first, it's just a matter. We could have the verifier go first and just make a dummy move. If we wanted to insist verifiers always go first. But the natural thing is it's for P to go first because P does the first interesting thing. So what P does is P chooses a random permutation. We already saw this kind of thing last week. This proof is going to be rather similar in some ways to the proof we had, the interactive proof we had last week to convince the verifier that two graphs are non-isomorphic. We're going to use rather similar techniques, but this time we're going to convince the verifier that the two graphs are isomorphic in such a way that we don't convey any information. So what P1 does is P1 chooses a random permutation which I'll call pi prime. And it sends V. So one of the points is what you communicate to the verifier, and it's going to communicate to the verifier what we get by permuting G2 according to the permutation pi prime. So we're going to use pi prime to shuffle the vertices of G2. So sends the graph. G3 doesn't see the permutation, but it just sees the shuffling that we get. This is similar to what we had the same phenomenon last week. So G3 just gets to see the graph, P prime applied to G2. Why does it apply to G2 rather than G1? Well, that's just helpful to make what follows go through easily. But let me just comment that from the verifier's perspective, it's somehow irrelevant whether the prover here chooses the graph G1 or G2 to put it here. Because we've got two isomorphic graphs and the prover is randomly permuting one of those two isomorphic graphs. If you randomly commute one isomorphic graph, is the same thing as randomly commuting the other isomorphic graph because they're isomorphic. And a random permutation is just going to give you another isomorphic, a random isomorphic copy of the graph, so to speak. But anyway, it works. Protocol works if P1 always does it with G2, so that's what we're going to do. So what the verifier does is the verifier responds to this by simply choosing a random bit. So I'm going to say a random number between 1 and 2. So chooses a random. Let me just stick to my notes. What do they call it? I. So either 1 or 2. With fair probability. So it tosses a coin. So I'll just simply write half probability. And what P2 does, P2 is going to now send the verifier back a permutation. But what permutation it's going to send to the verifier depends on I here. So if I equals 1, I need to get it right. We send permutation pi double prime that we get from composing pi prime and pi to the verifier. So this notation, I guess you all know, but it's function composition. And here we're just composing two permutations. Sorry, composition, not computation. But the other one, so else if I equals 2, which is the only other possibility for I, we send pi double prime, we simply let pi double prime be pi prime. And the point now is that P2 is sending, sorry, this is, I'm going to define this again to be pi double prime. We're sending a permutation pi double prime to the verifier. And the point is it's some permutation on the natural numbers that has a random component to it because it's got pi prime in it. And it may be that random component applied to pi, or it may also compose with pi, or it may not be. But because pi prime is purely random, we can't tell whether or not we've composed it with pi or not. What we get, what P2 is giving to verify from the verifier's perspective is just a random looking permutation. That's what the verifier gets. But it will either be a random looking permutation that's like this, or a random looking permutation that's like this. And what the verifier does is then checks that essentially the prover has followed the rules, so to speak. So the verifier checks, so that it will accept if what it checks is that the permutation it's got, if it applies it to the graph indexed by the random bit it chose I. So either G1 or G2, if it applies pi double prime to that, we should get back G3. So we can check this, we've got the graph, we can apply the whole permutation, we've got this permutation, we can apply the permutation to the graph, then we get an n by n matrix, and we simply check that it's the same n by n adjacency matrix we've got there, and reject otherwise. Right, and what I'm going to do now is state the 3 claims that tell us that this is a correct zero knowledge proof. So there are 3 important facts that come into this.
Right, so if P1 is worse than P2, is there any reason that P1 was before P1?
Well, that's a good question. I need to think about that. I never asked myself that question, and now that you ask it, it looks like a very good question. I don't, for the moment, see the reason. Let me keep it in the back of my head, and we'll go through the correctness statements, and let's see if this actually pops up. That's a very good question.
Also, I think you don't forget there's a table in whiteboard under this one that you can use if you want. Just pointing that out.
No, I know, yes, thank you. I know I've got the, but I want to put this stuff here because then I wanted to hang around for a bit. That's why I was running, that's why I'm overwriting this. I didn't want to go put this on the backboard and then immediately hide it, because this is more important. Yeah. Okay, so yes, I'm still thinking about your question, but let's carry on. So the 3 important properties are, the first one, the first 2 are going to be the same sorts of properties that we proved for an interactive proof. So the first one is, if indeed we start off with an isomorphism, and and P indeed is basing this on an isomorphism, then the verifier will accept with high probability, and in fact the probability that the verifier accepts here is 1. So if pi is indeed an isomorphism from such that pi G1, G2, and importantly, the prover behaves in the way we're saying it behaves, and P behaves correctly, behaves as specified, then the probability that the verifier accepts is 1. And this is obvious because we've chosen a random permutation, but because pi is an isomorphism, well, if P behaves as told, then if I equals 1, well, if I equals 2, that's the easier case, then indeed we're sending, P2 is sending the verifier pi prime, which was an isomorphism from G2 to G3. That's what the first step is doing. And if I was 1, then it's sending pi prime, which is an isomorphism from G2 to G3, composed with pi, which is an isomorphism from G1 to G2. So the composition is an isomorphism from G1 to G3. So in both cases, for both values of I, the prover is sending the verifier an isomorphism from Gi to G3. So this equality always comes out as true, and the prover certainly accepts. So the second case is to check, and again, so we had this kind of condition last week. Again, the second case, we're going to have a similar condition to another condition, which is the same as we had last week, which is we cannot fool, the prover cannot fool the verifier into thinking that two graphs are isomorphic if they're not isomorphic, or only with low probability. So for this one, we assume if G1 is not isomorphic to G2, then for any prover P star that interacts correctly with V in the protocol, so that interacts with V, as defined last week, so such that they're giving each other the right kind of values, then what I claim is that the probability that we want in this case V to reject, because the graphs are not isomorphic, so reject means I'm detecting that the graphs are not isomorphic, we want that to happen with high probability. So then G rejects with probability. And in this case, the probability is then we're going to write a half or greater than equal to, I guess it's exactly a half, because if they're not isomorphic, then no, that's probability greater than or equal to a half. Because prover might just be sending some rubbish here. We're having a prover P star, but all it needs to do is interact with it. It might be trying to deceive the verifier. So we can't guarantee that the prover is doing what it says it's doing here. All we can guarantee is that the prover sends some isomorphism, and we need to check whether or not the isomorphism we get back from the prover satisfies this equality. But because the two graphs are non-isomorphic, and we've chosen I with the toss of a coin, at most, this random permutation we get from the prover applied to if we apply it to two different non-isomorphic graphs, at most one of them can be isomorphic to G3. If one of them is isomorphic to G3, the probability of rejection is a half. If neither of them is isomorphic to G3, then the probability of rejection is 1. So this inequality always holds, no matter what P star does. And finally, the interesting condition, well, they're all interesting, but these two we had last week. But the new condition is the condition that P does not gain, sorry, the verifier does not gain any knowledge. So for this, we again assume that if pi is an isomorphism, so we're interested that the verifier does not gain any knowledge about the actual isomorphism that exists from G1 to G2. So if pi is an isomorphism, we're the same isomorphism such that pi of G1 of G2. And again, we can assume that we've got the actual official P. What we want is that the actual official P that behaves in this way, as specified here, cannot leak any information to the verifier. So we're going to assume that P behaves as specified. Then, well, how can we say that P does not leak any information? Well, let's so let me just basically paraphrase it at the moment, and then we'll come to a more precise condition. But let me just, there's one subtle point I want to bring in already now, which is we want the verifier interacting with Gruber. Through this interaction, the verifier doesn't learn anything from the prover. But we want something even stronger than that. This is the interaction the verifier wants to do if the verifier wants to understand that the two graphs are isomorphic at the end, or not. But if the verifier behaves like this and the prover doesn't leak any information, it still could be possible that the verifier could say, well, actually, what's more important to me is to learn some information rather than finding out whether the two graphs are isomorphic. So rather than behaving this way, I'll behave in a different way that's especially intended to get some information out of the prover. That would be a possibility. So what we need to say is that no matter how the verifier behaves, it does not learn any information it shouldn't from the prover. So we now need to consider an arbitrary verifier V star. So then no V star that interacts with P no, but I'm still avoiding the main technical issue at the moment. So I'm just going to put it that this for the moment learns anything about pi from the interaction. So this is something that's quite tricky to make mathematical sense of. So while I'm putting the border up, think about this protocol and try to think about why the verifier doesn't learn anything from it.
More time, I would turn this into a question and answer session and we try and work our way to the correct answer, but we don't have time to do it like that. So
the last point is formalized as follows. So we want to say no verifier can learn anything. Now, the one requirement we have on verifiers is that they are resource bound. They're supposed to be efficient. So the verifier will keep it polynomial time probabilistic. So it's for any probabilistic, for any p times probabilistic B star that interacts with P. The idea is that what the verifier doesn't learn anything because it can simulate the behavior of the prover to sufficiently well that it can't distinguish between the behavior of the simulated prover and the real prover, even though it doesn't know that the two, it doesn't have an isomorphism between the two graphs. So what does it mean to simulate the behavior of the prover? Well, we ask there to be another probabilistic time algorithm which will simulate the behavior of the prover. So for any verifier at all, there exists an expected p time probabilistic algorithm which we call S star, simulator, depending on V star, the whatever algorithm we've got that we're thinking of as a verifier that might be trying to get information out of the prover. So that simulates the result of the interaction of E star with P. So that what we have is that for all instances of the graph isomorphism problem, so all possible inputs where there is actually a graph isomorphism, what happens is that if we take the output, if we run the interactive proof using our tricky verifier, that could be the actual verifier, but might be a different verifier that's trying to get information, trying to trick the prover to give information, which it's not going to be able to do. If we run that protocol and look at the result of this, running the protocol of the prover against the tricky verifier, and see what the result is, either accept or reject. We run that on the input W, then this is indistinguishable from running the simulator on W. So the simulator, the important thing about the simulator, the prover has access to the isomorphism between G1 and G2. The prover will always have an access to an isomorphism between the graphs G1 and G2. And irrespective of that, the simulator doesn't. The simulator just gets the two graphs G1 and G2. And what we ask is that these are indistinguishable, which for the moment is going to mean that, so this is a probabilistic algorithm, so there's some probability distribution here over accept and reject. And again, this is a probabilistic algorithm, there's some probability distribution over accept and reject. And what this equivalence means is that it's the same probability distribution. Okay. The same probability distribution. And what I just want to end with before the break is to define this simulator. So this is, as you see, somehow the idea that you don't leak information, if you think about this, is quite intuitive. Trying to formalize it, it gets a bit technical. And actually, this is only halfway technical to the eventual final formalization we want to do at the end today. But after the break, we're going to start again with another zero knowledge proof for a different problem, which is again going to be going back to being more intuitive. And then we'll need to in the end, formalize the definitions we need for that. But before that, so I'm going to do a technical bit now. We don't have the break, and then we're going to start again with something a little bit more intuitive at the start of the second half. So I just want to end with defining the simulator. Defining S star for the GI protocol. And there is, maybe there's one other thing to say in general, that somehow there are two things to get one's head around in this subject. One is the definitions, which are already, the concepts of the definitions, which are already quite involved. Another is to do the proofs, which are really quite clever proofs in many cases. I've done plenty of proofs in the course already. So for this subject today we're going to just focus on understanding the definitions. And for the proofs, if you want to see them, you can look in the textbook, but they would take a substantial amount of time to do the proofs in lectures. But what we can do is understand the simulator without proving that it works. So the point is, we want to show for any sort of verifier that may be trying to trick the prover into leaking some information, we can find a simulator defined from the verifier. So given that we're allowed to use the verifier in the simulator, so given V star, we define S star as follows. So first, it takes the simulator takes an input, a word in the language, graph isomorphism. So it will take some G1, G2, oops, G2, such that G1 is isomorphic to G2. We're only interested in what the simulator does when it actually gets two isomorphic graphs. But importantly, it does not get the isomorphism between them. It's just given as input the two graphs. What it's going to do is it's now going to simulate the protocol between the prover behaving in the way the prover should prove and this tricky verifier we've got, that maybe the actual verifier or maybe some verifier behaving in some other way. So coming back to Nate's question here, this is actually the way this works is it now does invert the next two steps. So I will really need to think about this, I think, after the lecture. So what it does is it chooses a random J in 1, 2, and a permutation I double prime on the set of vertices, and defines G3 is I double prime of Gj. So S star randomly commutes. So randomly commutes according to a random permutation, one of the two graphs. It then gives G3 as input to V1, sorry, as input to V1 for round 1, as input to the verifier for round 1. So we run verifier V star in round 1 of the we run round 1 of this verifier V star, which follows the protocol. So as round 1 and 2 on G3 and obtain the result I of running the first round verifier. And now the idea of guessing the J here was to guess the I. We might have got it wrong. And if we got it wrong, we simply go back and choose another random J and carry on again. We're going to do this, repeat this step until we manage to guess the right J that the verifier also chooses. So if J is not equal to I, we go back to 2. But otherwise, if J equals I, then we simulate round 2 of V2 and return, which will either accept or reject, and return that as the result. So then simulate V star round 2 and accept or reject as so following what V star does. And essentially the main point here at a high level is that what we've done is we've followed this protocol, except whenever we needed a prover step, we just chose the information randomly. And then if we ever got to a point that it wasn't consistent with how the real prover and verifier would behave, then we go back and we start again until we get a consistent interaction. But I'm still puzzled by Nate's question, because those things have been inverted, but this would become easier, and we wouldn't need to do things in that order. So I shall think about that. It's 5 past now, so we shall have a 5-minute break until 10 past, and then start again, going back to something a little bit easier. Okay, I shall pause the recording. Right. Okay, so I want to start this last half with another example of a zero-knowledge proof. And actually, this is a very beautiful and intuitive zero-knowledge proof. And it's so sufficiently beautiful and intuitive that one gets it in sometimes in popular science videos, particularly in talks by Annie Vigdisson, the recipient of the Abel Prize this year. And this is a zero-knowledge proof to show that for an NP complete problem, and in this case we'll do the problem that the graph is 3 colorable. So zero knowledge proof. That graph G is 3 colorable. So again, P is going to start off with the secret knowledge that, well, it wants to verify that a particular graph G is 3 colorable. And P will know this because P will have a 3 coloring of the graph, but P wants to convince the verifier without leaking any information about the actual coloring. So now P knows a 3 coloring. So that's going to be a function from the set of 1 to n, the set of vertices. I'll just call the colors 1, 2, and 3. But P wants to keep this secret. So what P does is, so P chooses a random permutation of the colors. And the idea is that, so suppose we got some graph here. So remember, the usual graph formulation of 3 coloring, we're not just talking about planar graphs. We want to color vertices of the graph so that no 2 adjacent vertices have the same color. So for example, you might have a graph like this. Let's make it 3 colorable. I mean, I don't want to make it very exciting and big because I don't want to draw too much, but here's a 3 colorable graph, and P knows some coloring. So suppose the coloring that P knows is red, blue, and black. Well, let's make a nice colors. Let's use orange, blue, and orange. So suppose this is the coloring that's known. But P does not want to reveal that coloring, so it randomly permutes the 3 colors. So we might, so the random permutation might map red goes to blue, blue, I don't know, maybe, a random permutation, there are only 6 of them on 3 colors, so some of them are cycles, some of them are swaps. Let's do a swap. So suppose it's this one. So the permuted graph is, the permuted coloring is blue. The red and blue got swapped. So blue, red, blue, and this one's still orange. Now, obviously, P can't communicate this to V, because then the verifier would learn the 3 coloring, because the commuted coloring is still a coloring. But what V does is, what P does is it pops, makes a sealed envelope here, and it puts blue in the sealed envelope here, orange in the sealed envelope here, red in the sealed envelope here, so all the, and blue in the sealed envelope here, and it lays all these sealed envelopes on the table in front of the verifier. So the verifier doesn't see what's in, I'm letting you see what's inside, but the verifier does not see what's inside. The verifier just sees the envelopes. Okay, so let's see how I've written this. and exhibits to be a n sealed envelopes, one for each vertex, where envelope I contains inside it C of I. Sorry, permutation pi on the color rings of C of I. Okay, so that's what we've done. We've put the permuted color inside the envelope. So P then. So V now chooses a random edge. This should be in black if I'm keeping the same coloring, but anyway, never mind. It chooses a random edge. And with the uniform distribution over the edges. And then what P does, so suppose V chooses this edge. Some stars here. The edge being chosen. So then what the prover does is it opens these envelopes and shows what was inside. A bit like a conjuring trick or something. Secret information, and finally you're revealing it that was magically put there at the start. And P then swiftly removes all the other envelopes so that V is not allowed to look inside the other envelopes because V is not allowed to learn what the coloring is, but it just gets this edge. So P reveals to B contains the values of the two envelopes. So that's the values, the permutation applied to C of I and permutation applied to C of J. So this is the contents of the envelopes. I'm going to write that down. And then what V does is V just simply checks, was this plausibly a three coloring? Well, it certainly wasn't a three coloring if these two colors are the same. But if the two colors are different, and we've checked one edge, and if the two colors are different, then, well, of course, we might have selected the wrong edge, but nonetheless, if the two colors are different, that gives us some confidence that maybe it was a three color. Doesn't look like very much confidence, but we'll look at it quantitatively in a moment. So V accepts if these two values are different. So if we've got two different colors on the edge, and rejects if otherwise, so if they're equal. And that's it. And it never gets, importantly, the verifier never gets to look inside the other envelopes. And we're going to see a similar trichotomy that's split between three different things that we had for the zero knowledge proof that two graphs are isomorphic. We're going to have a similar trichotomy here. So let's put a line in the middle. So in this case, what we have is that if C is a 3-coloring and P behaves as specified, well, then it was a 3-coloring, so no matter what edge the verifier chooses, also V behaves as specified. I should have made that clear last time, but anyway, as long as P and V behave as specified, but V is trying to prove that it's 3-coloring, so trying to understand that it's 3-coloring, so we'll assume that V behaves as specified. And no matter what edge it chooses, of course, the colors are going to be different because it is a 3-coloring, so it accepts. So then V accepts with probability 1. If, on the other hand, G is not 3-colorable, then in that case, if it's not 3-colorable, no matter what the prover has put in the envelopes, there will be, I mean, it's only allowed to put 3 colors in the envelopes, but whatever it puts in the envelopes, there will be at least one edge that has the same color. So the verifier will reject with probability at least 1 over the number of edges. So then V rejects with probability greater than or equal to 1 over the number of edges, and that's greater than or equal to 1 over x squared, obviously. Well, it's actually greater than 1 over x squared because we're not allowing some edges from a vertex to accept. So that's a rather small probability of rejection, especially the definition of what are they called? Interactive proof last week required us to get the probabilities over 2/3. Here we've got a rather small probability, but at least it's something to work with. And as we're going to see, we can use the usual repeating trick to get that probability up to 2/3. But the last property is that, again, let's put it in red because it's the new one. If G is a G is so again, sorry, C is a 3-coloring. And P is as above. Then no verifier B star learns anything about C. From the interaction. This is the zero knowledge condition. And this is very intuitive in this case, because how could it learn anything about the colouring from the interaction when all it sees, from its point of view, it just sees a load of blank envelopes, it picks a random edge, it sees the contents of those 2 envelopes and it gets 2 distinct colours. That's all it sees. It always gets 2 distinct colours, but moreover, because these colours have been commuted each time, the 2 colours it sees are always just 2 distinct colours chosen from the random distribution, the uniform distribution on 2 distinct colours. There's no information there at all. It's very, very intuitive. But actually to formalize what's going on here requires quite a bit of machinery and quite a bit more than we use for the proof, for the zero knowledge proof of graph isomorphism. I mean, can anyone see what somehow the main computational issue we need to deal with here is? What in what I've told you is not obvious how to do with Turing machines?
To get probability for rejection up.
Oh, well, there's that. So we are going to address that. So that is an issue. Maybe we'll do that straight away, and then we'll. So that's the first thing to do on my list. So there are three issues. So the first one is boosting the rejection probability. But again, we're just going to do this by running a repeated number of times. We just have to repeat quite a few times. So for this, if we repeat the interaction n-1 times, is that right? Yeah, n squared minus 1 times. Then the probability. So we've got n squared vertices. If we test n squared minus 1 edges, then the probability that we will see at least one pair in which the colors are equal, because there doesn't exist at least one, turns out to be at least a half. And the probability that we reject at least once is greater than or equal to 1/2. And once we've got the probability to 1/2, then we can repeat it. We can do k times n squared minus 1 times and get it to 1 minus 2 to the 1 minus 1 over 2 to the k. So the reason for this is that for any n greater than or equal to 2, we work out. So if you look at the probability that we accept every time when there are n minus 1 out of n things that would give us to reject, then we will accept n minus 1 over n times. So I think of n being n squared here. If we've got a probability of n minus 1 over n of acceptance, we repeat that n minus 1 times, and we ask what's the probability that we accept every time. Then we're looking at n minus 1. So if we repeat it n minus 1 times, we get, well, let's put it like this, and we get this probability. So this is the probability that we accept every time if there are n minus 1 out of n possibilities of acceptance. And it turns out that this value is always less than or equal to 1/2. There's quite a simple calculation that tells us this. So this is 1 minus that, where n is n squared, and then that is greater than or equal to 1/2. Okay. So that issue we can deal with. Yes. Maybe I'll continue here. Let's keep the. No, let's do. Okay, so as I said, there are three issues to understand. What's the next one? So what's this protocol? What's not obvious how to do with the Turing machine?
Envelopes.
Sorry?
Envelopes.
The envelopes, yeah. So what do we mean by laying an envelope on the table? I mean, we can see that physically. If you've got an envelope in front of you, as long as you trust that the prover is not going to do any sleight of hand like a computer and swap the envelopes, you can can see the envelope there and wait for its contents to be revealed. But how can we do that with Turing machines? They can all they can do is communicate strings to each other. So you need to communicate a string that's like an envelope, and that string can be opened. So how do we implement sealed envelopes? That's the first question. Let me list the question. Sorry, that's the second question now. This is the one that I think is of most interest. And then there's the formulating the zero knowledge condition. And I don't really think I'm going to have time to do it properly today. But I think I shall just, well, we'll see how much we have time to do. But the thing that I think is of most interest is the next bit, which is how do we formulate these sealed envelopes? So anyway, issue 2 is how do we implement on the Turing machine or on a computer a sealed envelope? And question 3 is making the zero knowledge condition precise. Well, didn't we already do that with the zero knowledge condition? Well, we did make it precise, but actually the version we used before is not going to be correct for this protocol. We need a slightly weaker notion of zero knowledge for this particular proof, which is a better notion, really, of zero knowledge than the one we had, making the zero knowledge condition precise. But I want to really mainly focus on how do we implement sealed envelopes. And this is a little bit related to cryptography, which is a major topic in computer science, of course, and in applications, and also in complexity theory. We're not really going to touch on it that much. This is the main thing we're going to do with it now. So what we're going to use is a very important concept called a one-way function. And we're going to see how we can use a one-way function to implement sealed envelopes. The one-way functions are really pervasive in computational complexity theory and in many applications of theoretical computer science. So it's good to understand what they are. It opens the door to many other topics that depend on them. So this is a fundamental definition. The idea is a one-way function is a very intuitive thing. It's a function that's efficient to compute, but it's not efficient to compute the inverse. There is no efficient way of computing an inverse to the function. So a one-way function is just going to make it deterministic polynomial time computable. So it's a p-time computable function on strings. So it maps a string to a string, such that there is no efficient way of inverting the function. Now that's a bit tricky to formulate. Well, efficient, we know roughly what we mean. We're going to mean polynomial time. Because in practice one can use randomness, let's give ourselves as much possibility of inverting it as possible and say we still can't do it, even if we allow randomness. So we're going to say for every polynomial time probabilistic function, so such that for every probabilistic, for every p-time probabilistic algorithm, what we want to say is this probabilistic algorithm is going to fail miserably to compute an inverse to the function f. What does fail miserably mean? Well, it means it's got a very, very low probability of getting the right answer. So to say that, we ask, there's a technical concept we use, that's a negligible function, which is a way of giving us the low probabilities. So I'll define that in a moment. A negligible function epsilon of n such that for all n, well, it's just a function epsilon, but such that for all n, what happens is if we compute the probability over all input strings W in sigma to the n for our alphabet sigma that we're working with, the probability that if we apply A to f of W, if we apply A to f of W, so A is trying to compute an inverse to f. So if it did compute an inverse, if we applied A to f of W, we would get well, I don't know where I wrote it in this complicated way. So the probability that I don't know if this is more complicated or less complicated. The probability that this equals f of W is very small, by which we mean it's less than epsilon over n. So this is giving us sufficiently small probabilities. We'll see what this means. So what this is saying is, well, this will be true if A computes an inverse to f on input W. This will always be true. The probability that A actually finds an inverse to f on input W is very small, where very small means bounded by this negligible function. This is a really important definition. Let's put it in that red box. I need to say what a negligible function is. Function epsilon from the natural numbers to positive reals is negligible if epsilon n is dominated, is little o of n minus c for every c greater than equal to 1. I guess greater than equal to 0 is fine as well. So remember, this means dominated by is smaller for any constant multiple is smaller than a constant multiple of this function. So it's smaller than 1 over n squared, it's smaller than 1 over n cubed, it's smaller than 1 over n to the 4th. So all these functions shrink very quickly as n gets larger, and epsilon needs to shrink more quickly than all those functions. So it could be, epsilon could be 1 over 2 to the n, that would be negligible, or it could be 1 over n to the log n, that's a sort of slightly less fast growth, slightly less rapidly shrinking negligible function, but it needs to be smaller than 1 over any polynomial in it, essentially. So equivalently, there exists for all C, there exists an n, such that for all n greater than equal, little n greater than equal to the bound n, epsilon n is less than equal to n to the minus c. Anyway, the point is the function shrinks to 0 very, very quickly. And so, you know, as we go up strings of longer lengths, it becomes increasingly, it becomes very unlikely that we can invert the function. You can always invert the function on strings of short length. You can always make a special algorithm that will have a few special cases. But as you get to longer lengths, you can't keep on doing that indefinitely. And so eventually it's going to. Right. So that's a one-way function. Actually, we're going to, actually, before going on, let me mention a little fact. This will be an exercise, which is that if a one-way function exists, then P is not equal to NP. Or if you like, if P equals NP, then no one-way function exists. So this is interesting because one-way functions are going to be useful. We're going to use a one-way function in order to do these sealed envelopes, in order to implement these sealed envelopes. So it's going to be something useful we can computationally exploit, having a one-way function. One normally thinks of, I mean, when one first meets the topic of P is not equal to NP, one thinks of it, if this is true, one thinks of it as a negative fact. It means we can't efficiently compute some things we'd like to be able to compute, like the satisfiability problem. On the other hand, if P does equal NP, well then we can efficiently compute those, but in a sense we can efficiently compute too much. For example, we can efficiently compute inverses for arbitrary functions. And actually it's very useful to have functions that we can't efficiently compute inverses to. And that means it has to be the case. We're relying on P not being equal to NP for that to be the case. But given that what seems to be a fact of life, we can actually exploit it to do something useful. So no, it doesn't matter so much we can't efficiently compute SAT. What we can do is we can reap the benefits of the P not being equal to NP in other ways. So there are actually advantages to P not being equal to NP. So this is an exercise. And load up. So in cryptography and other subjects that fundamentally rely, the whole point of cryptography is being able to codes basically to be able to communicate with ciphers and encoded texts and encoded messages. And one can imagine that it's really important to that. The encoding function is hard to invert unless you know some secret that will help you to invert it. So it turns out to be very useful to assume that one-way functions exist. So we're going to make that as an assumption. But actually we're going to make a slightly stronger assumption, which is a one-way function of an important kind exists. That's a permutation. So a one-way permutation is a one-way function that further satisfies a one-way permutation basically means for any string length, it's a permutation on strings of that length. So a way of saying that is that it's injective. It's one-to-one. Any two different strings get mapped to two different values. And further, that f preserves the length of strings. So this guarantees that then f is a permutation on strings of the same length. So for all w, if you find the length of f applied to w, well, it preserves the length of strings, so that's just it. And we're going to make the assumption a one-way permutation exists. So it's an efficiently computable permutation on strings of any length that is hard to invert. This assumption is a little bit stronger, or nobody knows how to prove from the existence of a one-way function that a one-way permutation exists. But there are many candidates for one-way permutations. So people believe they exist. A one-way permutation exists. Given this, we can implement our sealed envelopes. I think I'm going to stop there after having told you how to implement the sealed envelope. The implementation is really nice and simple. But the proof that it works is really quite deep. And it's a beautiful proof. You can look at the textbook for it. As I said, I want to get mainly definitions in this part of the concept, rather than going into the proofs, which are rather technical in this part of the course. But anyway, if you're interested in this sort of material, then I highly recommend this proof. So the sealed envelopes work by what's called the Goldreich-Levin theorem. And this says, suppose f is a one-way permutation. Then, for any probabilistic p-time algorithm, A, there is a negligible function epsilon such that probability over a randomly chosen W bits of length n and a randomly chosen R, the bit vectors of length n as well. So two randomly chosen bit vectors. Probability that if we apply our algorithm A to the two inputs fx and r, probability that that is the dot product of the two vectors, that the scalar product, scalarly product of the two vectors modulo 2, that's why there's a circle around it, we're talking about bit vectors, is less than equal to a half plus epsilon the length. So as the strings get longer and longer, this gets extremely close to a half. It looks a bit mysterious, but what it's saying is we choose two random strings here, and we apply the one-way function to one of them, and they're of the same length. Then this value, this bit value computed from the two random strings, we can think of these two random strings, so this should be W. This should be W here. We can think of these two random strings as storing this bit value. And these two random strings we think of when we apply the one-way function to one of them, this pair is our sealed envelope, because we can't get the information about, so this is the value we're hiding, this scalar product. And we can't get that information from f of w and r. We need w and r to get this information out. And the fact we can't get this information out is saying whatever algorithm, whatever efficient algorithm we apply to try and get the information out, well, it's basically going to give us very close to just a random answer. Okay, so let me, so WR, W, circle R, is defined to be scalar product, dot product, modulo 2. So, dot product, 2 vectors. And so, how we use this for sealed envelopes, implement the sealed envelope containing a bit, a secret bit that we want to. The point is we've got. So of course we were using 3 values in our 3 coloring example, but if you can store 1 bit, then you can obviously store 2 bits and you can code 3 values. So the point is, our sealed envelope, we're saying we're putting this value in it. We want to give information that when we decide to reveal the contents of the envelope, we can prove that this was the bit we had in mind. We can't trick. We really put this bit in the envelope and give enough information that then when we reveal the bit, the verifier can verify it's really there. So what we do is we pick a large enough n. I'm not going to talk more about what that means, but and then we randomly generate W and R bit strings of length n such that dot product is the bit that we're trying to hide. So it's easy to randomly generate strings, and with probability half, we're going to get the right bit. So sooner or it's not going to take us very long to randomly generate a pair that hides the bit. So then we make the pair f of W are public. So this is called this is the sealed envelope. So we're saying we've got a bit. We're not telling you what it is, but we're giving you the information there that if we choose to reveal the bit in the future, we will be able to prove that that really is the bit that's in the envelope. And then to reveal the contents, we simply then give W, and then we can then the verifier can compute what the value of W naught R is. So to reveal the bit, and can compute f of W and check that the W we give really does indeed, it really is the key to getting this bit out of the envelope. So to reveal the bit, reveal W. So this whole process is not normally referred to as sealed envelopes, it's referred to as bit commitment. We're committing to a bit without revealing it. So the name of this process is bit commitment. But as you can imagine, it's a very, very useful thing to use, and we can use it directly to implement the sealed envelopes in our interactive proof for interactive proof, zero knowledge proof for graph. And just to
say the last thing to make the zero knowledge condition precise.
We had this before, we earlier saw this with the two probability distributions needed to be identical. That cannot be made true for the proof for the three colorability using this way of implementing sealed envelopes. It's simply not possible to do that. To be able to simulate the probability distribution so that the simulated probability distribution is the same as the one that one gets from interacting with the proof value. It's not possible to simulate that. What it is possible to do is to get the probability distribution sufficiently close that it's not possible to efficiently distinguish between the two probability distributions. So the correct thing is the simulator simulates a probability distribution that is computationally indistinguishable from the one given by interaction with the proof. That is computationally indistinguishable. Let's do this. Computationally indistinguishable from the one given by B star interacting with A. As you can imagine, there are some technicalities to do with how one describes computationally indistinguishable, but we've run out of time, and in fact I've more than run out of time. So it's 9:58 now, so we'll have the 10-minute break before the presentations while we set ourselves up. So we'll start again at 8 minutes past 10. Okay, and hopefully if everyone sticks to the 25 minutes, then we'll be okay. I'm sorry I've overrun. Anyway, goodbye for now, and let's start.